Hello everyone! Recently I've been experimenting a bit with fractals and I thought it might be a good idea to create another effect that uses colors changing over time. The result is what you can see in the background right now, and this pattern can be modified in various ways using parameters. And that's precisely what we'll be creating in this video. This time, we won't apply the effect to an existing image. Instead, we'll generate it entirely on a black background. So I'll create a new scene and set everything up a bit differently than usual. But it won't be anything new for those who have been following this channel for a while. Okay, so creating a new scene. And this time it will be user interface. Let's call it fractal. Flower. Okay. And as you may remember, we will add a new child node of the type colorrect, which I will then set to a black color and change its dimensions to full HD. So it is 1920 by 1080. Okay, let's just make it fit to the screen, and scrolling down to the material section where I create a new shader material, click it and create a new shader, which is of course type shader, mode canvas item, name is fractal flower, and I will put it to the shaders folder. Create and click again to open it in the shader editor. And as always, I'll delete everything from the generated code that we won't need for our effect, leaving only the fragment function. Deleting vertex, deleting light, and Ctrl S to save. Okay, so this time we don't have an image available from which we could determine the resolution. So instead we'll add a uniform parameter to define it. And as we could see at the beginning of the video, this will be an animated effect. So we'll also add a parameter to define the speed of this animation. So let's add them to the code. Uniform vec2 resolution, and let's set the initial values to the full HD resolution, 1920 by 1080. Okay, and the second one, as I said, it would be float for speed. Float speed with a hint range, and let's set the initial speed to 1. And the range, let's put it from 0 to, for instance, 10 with a step point 0,1. Okay, and we can write the basic version of the fragment function. The effect we are creating will be symmetrical around the center, so we'll start by shifting the origin of the coordinates to the center. Because we are working with UV coordinates, that is in the range from 0 to 1, it's enough to subtract 0.5 from the UV variable. Let's expand this editor a little bit and write the first line. Vec2 UV is, as I said, UV minus 0.5. Okay, next we want the effect to look the same regardless of the dimensions of the element, in our case the colorrect. So we'll recalculate the aspect ratio using the usual formula. UVX is multiplied by resolution X divided by resolution dot Y. Okay, we continue by defining a time variable. As we know from previous tutorials, it will depend on the internal time and the speed parameter. So float time is time times speed. And finally, we'll prepare an accumulator into which we'll gradually store the results of individual iterations so that we can assign it to the output variable color at the end. Let's do it. Vec3 result is Vec3, and let's start with the black color. And finally, color, the output is vector4 which consists of our result, the first three RGB components, and finally one for the alpha channel. Okay, excellent. We have a very nice black screen into which we can start adding something visible. And because our effect begins at the origin of the coordinates and spreads out at different angles and distances, polar coordinates will be very useful to us, which we calculate according to the usual formula. Okay, and let's continue after the result definition. So right here, vector 2, let's call it polar, and it is vector 2, first the angle, which is a tan of UVX and UVY, and the distance, simply length of our UV vector. Okay, by the way, if you've never encountered polar coordinates before, I recommend watching my tutorial on this topic. You will find the link in the description of this video. And let's continue. I mentioned iterations, which we'll implement in the form of a loop, where we'll change parameters on each pass and store the result in the accumulator. But we need to know the number of such iterations, so I'll add a uniform parameter called iterations. Uniform float iterations with another int range, and let's start with just one iteration. Sure, why not? And it goes from 1 to, let's say, 10 again, and this time the step is, of course, just 1. We don't want any fractional iterations. And I'll insert the skeleton of this mentioned loop into the fragment function right after this. For float I starts at 0 and the number is the number of iterations and I++. Okay, and let's create an empty loop for the time being. Okay, so that was the easier part. Now we'll program the actual calculation, and I'll say it right away that I arrived at most of the formulas you'll see through trial and error, because there are so many possible combinations that it probably wouldn't make sense to try to come up with the final formula purely through logical reasoning. So it's not that important anyway, since many effects are based on prior experimentation. What matters is something else. To understand the basic principles on which practically all these effects are built, let's recap what we'll use and why. So first, trigonometric functions like sine or cosine for periodic repetition with smooth transition. The fract function for repeating patterns with sharp transitions. The exp function with a negative parameter for gradual brightness attenuation. The length function to change color based on distance from the center. The abs function for mirroring. The reciprocal value for curved shapes. A shift by 0.5 for symmetry. And finally, occasional addition or multiplication by an arbitrary constant to fine-tune details. That's quite a lot, isn't it? However, I think I described the meaning of something from this list in almost every tutorial, so this time we have everything in one place. The only things missing are a rotation matrix for turbulence and the mix function for interpolation, but we won't need those this time. So let's start writing code. First, we'll obtain the angle from the polar coordinates, in which we'll use them to divide the screen into the corresponding number of segments. And because we'll want to vary this value, let's add a new uniform parameter called slices, scrolling up to the uniform parameter section, and uniform float slices with a hint range, and we'll start with 10 slices, for instance, and the range from 1 to, we can now use, for example, 100, and the step again, just 1. Okay, and now the first line in our loop right here. In each iteration, we want to increase the number of segments, so it will look like this. Float angle is polar x times slices plus I. Okay, so polar x, as we know from this definition, is the angle, the aton result, and we multiply it by the number of slices increased by the current iteration index, which goes from 0 to the iterations minus 1. Okay, and let's continue. As I said, the effect is based on a mirror symmetry and repetition. We'll use both absolute value and sign and assign the result to the new variable called shape. A float shape is absolute value of sine of the angle. Okay. Then we want to work with the distance from the center, which we'll obtain using the length function. So float dist for distance is, as I said, length of UV. We cannot use distance because distance is a number of functions, so it cannot be reused as a variable name. Okay, and we'll also need a color to multiply the resulting value by. In the final version of the shader, we'll have a palette that changes over time, but for now, we'll make do with a constant color, so let's set it to red. Vec3 color is Vec3, and one for the red channel, 0 for green and 0 for blue. Okay, and now we multiplied everything and added to the accumulator. So result is increased by color times dist times shape. Okay, and we have some first result. It's nothing spectacular yet, of course, but we've managed to create a foundation that we can shape further. So we can try how our parameters affect the resulting form. Let's find them in the inspector, and speed is not used yet, but iterations are. Let's increase them. Yeah, and it's definitely changing. Let's get back, and the number of slices affects the number of these black rays. Very well. So now it's time to make a few adjustments. It looks like our effect is too dark, so we'll try increasing the value of shape by 1 to achieve lighter shades. Okay, and it's very simple. We'll simply adjust the shape definition by adding 1 to the result. Yeah, that's much better. Next, it would be good to emphasize the ends of these rays, like they just fade out too much. So that we get more uniform lines that we can shape further later on. So in here, in this definition, we will multiply it by x of the negative argument, in this case the length, so polar dot y, and let's multiply the result by the shape value. Yeah. And now comes the first magic trick. In each iteration, we'll modify the UV coordinates using the fract function, which ensures repetition of the pattern in the x and y directions. We'll add this line before defining the dist variable. So right here, UV is fract of UV times shape. Okay, and we can see that we need to do something to fix the symmetry. The solution is simple. The fract function returns values in the range from 0 to 1. So if we subtract 0.5 from the result, we get a symmetrical range from negative 0.5 to 0.5, like this. Minus 0.5, and wait for it. Yeah, perfect. We've obtained a much more interesting result. But we are not finished yet. You surely remember that the effect we want to create contained variously curved and distorted lines. For this final calculation, we'll prepare one more uniform parameter. Okay, let's scroll up again and create it. Uniform float. This time let's call it warp with a hint range, and the initial warp would be 10. And it goes from 1 to 100, and the step can be 0.1 this time. Okay, and now pay attention. the second magic trick. I'll add a formula that looks terrifying at the first glance, but in reality it's again an application of the basic principles I mentioned. Specifically, it involves absolute value, sign, reciprocal value, and multiplication by a constant. The result of experimentation looks like this. So right here, we will modify the dist value further. Dist equals 0.01 divided by absolute value of sine of dist times warp plus angle, okay, divided by warp. This is nice. And we can verify that the warp parameter really influences the overall shape of the effect. Let's do it here. So let's change to warp. Yeah, it's definitely changing. Great. Okay, so I think it's time to animate this effect. It will be very easy. We'll simply add the time value to the final formula. And let's do it here. Angle plus time, wait, yes. It looks quite nice, don't you think? One last detail remains to be solved. Applying a variable color palette. We've done something similar before, and at that time I used a well-known function for generating colors using 4 input parameters and a time variable. And to save time, I copied the parameters and the function from one previous shader, and I'll insert them into our code. Okay, and let's expand this window for now and insert it right after the uniform parameters section. So I added 4 uniform parameters of vector3 type ABCD, so 4 colors, and a function called palette, which uses this formula to calculate a color based on these parameters and the time variable and returns vector3, so color in the RGB format. Okay, and now when we use the new palette function to define the color in the fragment function, we'll get the final effect. Let us get back. And so that the colors change nicely, I use as parameters the distance of the pixel from the center, and then the index of the current iteration and the time variable, and I'll slow everything down a bit using a constant like this. So there, instead of static color, we'll use the palette. Its parameters polar y, the distance, plus shape, plus I, the iteration, plus time, and times 0.1 and the semicolon, sorry. I think we can be satisfied with the result. So let's try setting a different color palette by changing the uniform parameters, and we can also play around with the other values. So here are the ABCD colors. So what if we change this gray to something greenish or pinkish? Yeah, it definitely has the impact, or this one. Okay, I think it was even, maybe it was better with the default values. Anyway, what happens if we, for instance, reduce the number of slices to 1 and increase the iterations? 5, 6. Yeah, this is pretty cool, isn't it? We can definitely find many interesting combinations with these parameters, so I leave it up to you for further experiments. Thank you very much for watching. I'm not sure how usable such an effect is in games. Perhaps it could be applied as a screensaver of the monitor that the protagonist has in their office. The purpose of this tutorial was rather to demonstrate that experiments based on basic principles can bring surprising results, and the possibilities of achieving them are practically unlimited. Of course, we mustn't overdo it with the number of iterations, but as we could see, even with a small number of repetitions in a loop, very nice effects can be achieved. And as always, I'll add this shader to the Godot shader pack product, which I link in the video description. For now, take care, good luck with your experiments and projects, and I'll see you in the next video.